The third and final section in the growth models chapter deals with what are called logistic models. Logistic models are similar at the beginning to exponential models, but it turns out over the long run they make better predictions than exponential models, at least in population growth problems. So we illustrate this with an example with the world population, and without going into too much detail, if we use a few data points to create an exponential model, like the ones we saw in the last example or the last section, we can make predictions with this. And in the short term, or maybe the medium term, they are fairly accurate. But if we make long-term predictions, they start to get really, really unusual and ridiculous. So, for instance, if we predict the year 2005, which of course we know the actual population, the model predicts that it will reach just over 7 billion, and the actual population was 6.5 billion. Not great, but not terrible. But if we predict forward to 2015, which we do know the population, this model predicts 8.5 billion, and the real population is really only 7.3 billion. So the model is getting worse as you predict forward in time. And that makes sense. The longer into the future that you try to predict, the more error you're introducing into your model, into your predictions. So the model is performing worse and worse over time. And again, the reason for this is that the growth rate in the population isn't actually constant. An exponential model assumes that it is, just for simplicity's sake, but really it's not. Really the growth rate might increase or decrease at different points in time, and it seems right now that the growth rate is slowing. And the reason for this is that there are, in any environment where you're growing a population, there are limited resources. And as those limited resources put a cap on what the population can be, so as the population nears that point, it slows down and levels off. So the punchline is that exponential models aren't good enough in the long term because they don't account for limited resources when we're dealing with population growth. So logistic models take that limitation and they account for it by accounting for those limited resources, those constraints. So we mentioned the carrying capacity here, which is sort of the limitation on what the population can reach. It's just a maximum sustainable population. Without going into too much detail, we're just given this logistic model. And it looks more complicated than the exponential models. So the problems that will work might be a little simpler. But it's really not all that bad. Notice, though, that there is something exponential happening here. That's why I said it's based off of an exponential model, because there's still an exponential piece here, but there's just a lot more also happening. And if we think about the history of this model, sometimes it's called the Verhulst model, because this Belgian mathematician used it to predict the world population. And he used data from 1790 up through 1840 to build his model, and he published this model in 1838. So he was predicting forward in time. He wasn't looking back and trying to fit the world population to a model, but instead he was predicting forward. And it's only now, looking back, that we can see how good his model actually was. So if you build, with these data points, you build his model, that's what the graph of his predictions look like, and these dots represent the actual data he was working with. And now, looking back, we can fill in all the data after that point, and if you fill it in, you notice how closely it follows that line. And you can even see up at the top where it's starting to level off, just like the curve predicted it would. And that's really amazing to see a model that's predicting forward that far in time and ends up with results that are really that accurate. Quite impressive, and that gives us confidence in this logistic model, that it really does predict population quite well. So here's a simple example where we have the rabbit population, and we're given some information, we fill in the model, and then we can graph what that prediction line looks like. And notice that the curve starts to level off when it nears 2,000, the maximum sustainable population, or the carrying capacity. Once it gets close to that point, it levels off, and it's not gonna tip over that, unless something changes. Something could certainly change that would change that carrying capacity if the environment increases or gets more food, or a predator dies out or something that could change. But assuming that doesn't change, this model will level off, or the population will level off. And then we do another example with lizards, just to get more practice with this. Again, we're given information on the carrying capacity. This one has a much higher growth rate, so the initial jump is much sharper, and so the population jumps up very quickly and then levels off again at the carrying capacity. So in the long run, we expect the population to hit 1,000, because that's the carrying capacity, and it's growing right now. So we expect it to reach that point, but not to exceed it. So that's an example of how to take a logistic model and take given information and fill in the model and then make predictions with it.